The purpose of this module is to give you a basic understanding about computer languages and the number system. This module covers the following concepts of computer languages and the number system: hardware and software, computer languages, connection with programs, stages of program execution, number systems, conversion to decimal number systems, conversion of decimal numbers to other number systems. In Class 6, you have already learnt that a computer system is made of two main components, hardware and software. In this chapter, we will learn about computer languages and different number systems. Hardware and software. Hardware comprises the physical components that make up a computer system. You can touch and feel the hardware of a computer. Software is a set of computer programs that provide instructions to the hardware on what to do and how to do it. There are many languages that can be used to create programs to instruct a computer system. While writing a program in a particular computer language, the symbols of the language must be used as per a set of rules known as the syntax of the language. Computer languages can be classified into three categories: machine language, low-level language. In machine language, each instruction is written in the form of a string of zeros and ones. Programs in this language are directly understood by the computer, but are difficult to write. Programs written in machine language are executed quickly by the computer because the instructions can be processed directly by the CPU, and no translation of the program is required. Because the internal design of computers can vary from each other, a program in machine language will be different for different computers. Therefore, machine language is machine-dependent. Assembly language, low-level language. The first programming language close to the English language is assembly language, developed in 1950. Programs in assembly language are easier to write than in machine language, as each instruction is written as a set of letters. Each set denotes the operations to be performed and the addresses of operands. Assembly language is also machine-dependent. The programmer must have detailed knowledge of the structure of the computer for which the program is being written. An assembly language program written for one computer may not be used in another computer. High-level languages. High-level languages are close to the English language. They use English words, mathematical symbols, and numbers. They are machine-independent. That is, a program in a high-level language can run on different types of computers with little or no modification. Examples of high-level languages are Java, C, C++, C Prime, Python, Visual Basic, Delphi, Perl, Ruby, and PHP. The computer hardware only understands machine language. Therefore, programs in high-level languages must be converted into programs in machine language before they can be executed by the processor. Program written in a high-level language is known as the source code, and the converted program in machine language is known as the object code. The following are programs that can be used to convert a high-level language, or even assembly language, to machine language. Compiler. A compiler is a software that translates all the instructions of a source code into an object code at once. It also reports errors found in the program along with their line numbers. The object code produced by the compiler can be permanently saved for future reference. Interpreter. An interpreter is a software that translates one statement of a source code into object code and executes it. It then does the same for the next statement and proceeds in this way until all the statements in the program have been translated and executed. An interpreter is a smaller program than a compiler. The object code produced by the interpreter is not saved. If the same instruction is executed again later, the process of interpretation is repeated. Note that a compiled object code runs faster than an interpreted code. This is because compilation is done just once for the entire program, whereas interpretation is done for each instruction at runtime when the source program needs to be executed. Linker. A linker is a program that combines one or more object codes generated by a compiler into a single executable code. Assembler. An assembler is a program that translates an assembly language program into machine language program. The process by which a computer program is executed by a computer system is called program execution. It usually consists of the following stages. Pre-processing. In this stage, a preprocessor processes the source code and prepares it for compilation. Compilation. The preprocessed source code is passed on to the compiler. The compiler compiles and checks the code for errors and generates the object code. Linking. The linker converts the object files generated by the compiler into a single executable program. Loading. The program is then loaded onto the primary memory of the computer system, where it gets executed by the processor. While programming languages such as C and C++ use compilers, languages such as Python and Ruby use interpreters. The differences between a compiler and an interpreter are given below. A number system is a way in which numbers can be represented. There are many ways of representing numbers. Each of these gives rise to a different number system. There are 4 common number systems: binary, octal, decimal, and hexadecimal. Let us learn about them in detail. Decimal number system. The decimal number system is what we use most commonly. It is composed of 10 numerals: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Using these digits, you can express any quantity. It is also called the base 10 system because it uses 10 digits. The base number, 10, is also called the radix. The decimal system is a positional value system, also called the place value notation, in which the value of a digit depends on its position. For example, consider the decimal number 342. The position of the rightmost digit is the ones position. 100 equals 1. The numeral in that position indicates how many ones are present in the number. The next position to the left is tens, then hundreds, thousands, and so on. Each digit position has a weight that is 10 times the weight of the position to the right. The rightmost digit has the least positional value. Therefore, it is called the least significant digit, LSD. The leftmost digit has the maximum positional value. Therefore, it is called the most significant digit, MSD. In the number 342, 2 is the LSD and 3 is the MSD. Binary number system. When we type a character on the keyboard, the computer converts and stores it in the form of a string of zeros and ones. The symbols 0 and 1 are together called binary digits or bits and form the binary number system. The memory of the computer can be thought of as a vast group of cells. Each of these cells contains one bit of information, 0 or 1. The computer system is designed on the binary number system. The binary number system has a base of 2. It has only 2 digits, 0 and 1, and can represent any character with these 2 digits. The binary number system is also a positional numbering system wherein each binary digit has its own value or weight, which is expressed as a power of 2. Consider a fractional binary number, 1101, 1011. For a binary number, the binary point separates the whole number part from the fractional part. The place values of the digits to the right of the binary point are obtained by raising 2 to successive negative powers. Octal number system. The octal number system has a base of 8. It has 8 digits, 0, 1, 2, 3, 4, 5, 6, and 7. Each digit of an octal number can have any value from 0 to 7. The octal number system is also a positional numbering system. Each octal digit has its own positional value or weight, which is expressed as a power of 8. As an example, consider 1352.12, an octal number with a fraction. As in the decimal and the binary number systems, the radix point separates the whole number part from the fractional part. The place value of each digit to the left and the right of the radix point is equal to 8 raised to the successive positive or negative powers respectively. Hexadecimal number system. The hexadecimal number system has 16 as the base number. It has 10 numeric digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 6 letters, A, B, C, D, E, F, where A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. The hexadecimal system is also a positional numbering system. The value of a hexadecimal digit is expressed as a power of 16. As an example, consider the hexadecimal fractional number A3B.12. As shown below, the place value or positional value of each digit is a power of 16. Importance of the binary number system. The binary number system is important because it is used in designing computer systems instead of the decimal number system. Computers use binary number system for storage and manipulation of data. As you know, the binary number system consists of 2 digits, 0 and 1. These digits can be easily represented using switches. A computer has a large number of switches. A switch in the on state represents 1, while a switch in the off state represents 0. Any number can be stored using a group of switches which can be in on or off states. For example, a group of 8 switches can store 256 numbers from 0 to 255. The steps to convert a number from binary, octal, or hexadecimal number systems to the decimal number system are: find the positional value of each digit. Multiply the digit with the positional value. Sum up the products calculated in step 2. The total is the equivalent value in the decimal number system. Conversion of binary to decimal number system. A binary number can be converted to its equivalent decimal number by adding up the product of each digit value, 0 or 1, and its positional value as shown below. A decimal number can be an integer or a mixed number with an integer part and a fractional part. Therefore, there are 2 processes for converting a decimal number into any other number system, one for the integer part and the other for the fractional part. Integer part. This method involves repeatedly dividing the integer by the new base until the quotient is 0 and recording the remainder after each step of division. Finally, when no more division can occur, write down the remainders from bottom to top. Fractional part. Multiply the fractional part by the new base. Record the integer part if any, else record 0. Repeat step 1 with the fractional part of the previous multiplication, and then repeat step 2 until the fractional part becomes 0. In case of infinite calculations, generally 3 digits are taken.